Hi, in this video, I want to introduce you to what are known as potential barriers in quantum mechanics. And what I'm going to do is describe a scenario, like a physical situation, so you have something to think about in terms of like a physical thing happening. And then I'm going to describe the difference between what classical physics is going to predict and what quantum mechanics predicts. And the point is quantum mechanics predictions are really, really different. So I'm going to tell you about the predictions in this video, and then in subsequent videos, I'm going to describe why or how quantum mechanics makes those other predictions. So the particular physical situation that I'm imagining is kind of reasonable. Like if you imagine a piece of metal or some sort of material that you charge positively here, and another one just like it a little bit below, what we're going to imagine is taking another positively charged particle, which is repelled from these two plates, and imagine giving this charged particle a direction of motion towards the hole or the gap between the two plates. I'll say that's called the x direction. And imagine giving this particle different amounts of energy, right? And you know that the energy is a combination of this particle's kinetic energy and this particle's potential energy. So this is the energy of this particle, right? The potential energy is the energy of interaction between this positive charge and these positively charged plates, right? So this potential energy is the potential energy associated with the relationship between this moving charge and these stationary plates. So what I've gone and done is I've drawn a rough sketch of the potential energy of the interaction between this moving charge particle and the charged plates with a hole. And you know that because of the repulsion, the amount of potential energy is going to increase bigger, bigger, bigger as you get towards the middle, right? At which point the charged particle, actually it's going to have some large value somewhere in the middle. And then the potential energy is going to decrease on the other side. So this doesn't mean that the particle necessarily makes it through the gap. It's more like if the particle were at position X, we would say that the particle or this system has potential energy U of X. And just because of the symmetry of the charge distribution here, right? It'll be symmetric around x equals to 0. Okay, so for classical physics, actually the problem's sort of easy to understand in terms of energy. So if this particle has an energy that is bigger than this potential barrier's height, which I'm calling U max. So if the energy is bigger than that, we expect what that means is, right, let me outline this in red. So if the energy is bigger than U max, then that means the energy has some value that's kind of like this, right? I'm putting it above the barrier. So this is the red energy. But if we have less energy, right, what if let me make it black so it's the same. But the energy story is a little bit different seeming if we say that the energy is actually smaller than the maximum height of the barrier. So let me outline that in blue. And so, right, so U max is here, so I'm imagining that the energy is some value below. like this, right? So here's two possible energies. The red energy level, or the energy line, represents our little particle coming in hot, right? It's got a lot of kinetic energy. But the blue one represents the situation where our little particle is maybe ejected by some cold object with a small amount of kinetic energy. So here is the statement of what, in classical physics, what energy is going to dictate happens. So if the energy of our system is smaller than U max, then we are guaranteed that so this is the situation of the blue line, right? If the energy is smaller than U max, we don't have enough energy to be above the barrier ever, then we expect reflection to happen, which means our particle is going to get closer and closer to this position here, but as it does so, it slows down because its kinetic energy is decreasing and its potential is increasing. And at some point, all of its energy is purely potential energy. Its kinetic energy has gone to zero. And because of the shape of this potential, the force on the particle by this potential is backwards, remember? So don't forget that there's a basic relationship, that the force associated with the potential in a certain direction, x, is the derivative with respect to x of that potential, but with a minus sign. So you can see that right here, the derivative is positive, but when you tack on the minus sign, right, minus that positive slope is a negative number, and so the force is negative, and you understand the force in the x direction being negative, being a pushback on our particle, right? That's the force on that particle. So let me get rid of that. Okay, so, but the thing is, though, is it truly dictates in the sense that we are 100% confident that every particle that comes in with an energy below U max, we are 100% confident that it's going to reflect. It will not make it through. And at the same time, we are 100% confident that it's got no chance of getting through, right? No chance of transmission. But if the energy is actually above that potential barrier height, right? Now it's the red case where the particle comes in hot, right? It's backwards. There is no chance that this barrier is going to reflect the particle, because when the particle gets to here, it's got non-zero kinetic energy. So it has not lost all of its rightward directed motion. So there is no way that it will reflect, because its motion is never removed to the point where its motion is backwards. And the chance of transmission is 100%. And these are the two chances. And of course, there is the what if E is U max. This actually is strange. Classically, what that means is that we have a situation where the particle precisely has the energy to be able to make it to the top of the hill. But if you think about it, as it gets there, it loses its kinetic energy. And when it does get there, it doesn't have any kinetic energy anymore, which means it can no longer move, right? And it gets stuck there, actually. So that kind of situation in a real life scenario, that's really hard to achieve. That's called an unstable equilibrium. And that's just not something that people see, right? Because of uncertainty in measurement, for one thing. So not even classically can you achieve that. It's highly improbable, this mid case. So actually, I don't think it's worth it to bring it up at all. so I'm not going to bring it up. Oops. Okay. Cool. So that's the classical physics. The classical physics is either it goes either it goes past or it doesn't, and there's nothing else, right? What we're going to see in quantum mechanics, though, is all of these numbers are going to be in between 0 and 100. But we're still going to have either the particle reflects or transmits, but it could be 50-50. It could be 70-30, right? It could be 60-40. Okay, so here is the prediction in quantum mechanics instead. So in quantum mechanics, if the energy is colder or less than Umax, classically the particle is going to only reflect. The truth is there is a fraction, I'll call it f, right, that makes it through, and the fraction is guaranteed to be bigger than 0, right? That is, the transmission probability will not be 0. If E is bigger than Umax, oops, actually, I forgot. I wanted to do, so in the case where the energy wasn't enough classically to go up and over the barrier, nonetheless, quantum mechanics predicts that there is a fraction that will transmit that's bigger than 0, and there is a reflection component as well. And the reflection is 1 minus f, right? So if this fraction is, say, 20%, then this has got to be 80%, right? Because the particle is either going to transmit or reflect. But in quantum mechanics, these numbers are in between 0 and 100%. Okay, so that's the cold case, where the surprising thing is this transmission, even though classically we don't have enough energy. And this is referred to as tunneling. And sometimes you dress it up by saying it's quantum tunneling. And this is the idea behind a couple of pieces of technology, including the scanning tunneling electron microscope. So this scanning tunneling electron microscope is abbreviated STM, scanning tunneling microscope. So in this microscope, it's electrons that we're considering being the little projectiles. And the idea is we're trying to make it so that this is always the situation for the electrons in the microscope. And we are looking at, we're looking for the tunneling, right? And information from the tunneling, right, tells us about the landscape that we're looking at very closely. It tells us about the topography of a surface. Okay, so remember up here, we did that case, no surprises, this is what we're used to. So here is the new quantum mechanical surprise, that even if we don't have enough energy classically, quantum mechanics predicts that there is a non-zero probability to go ahead and transmit. That transmission, though, is genuinely a probability. So every particle coming up with energy smaller than Umax, some of them can be found on the other side, but all the rest have been reflected. So what's interesting, though, is also to think about this situation where classically all the particles were hot enough to make it up and over the potential barrier. And in that case, Remember that classical mechanics says that the transmission rate is going to be 100%. Like, right? The particle is definitely going to go over the barrier because there was never enough of the potential height to block the particles from crossing over. But in quantum mechanics, again, actually, it's not 100%. Even in the case where the particle classically clearly has enough energy to go up and over, it's still going to be a fraction that transmits. And this potential barrier, even though it's not classically fully a barrier, it gives us, in quantum mechanics, a non-zero probability to reflect off of it. And this is also very exciting because classically this is not the prediction. It seems like if you have enough energy, then you should be able to make it over, no question. But quantum mechanics actually predicts that you're going to have a reflection of some fraction of the sort of equivalently prepared particles. So this is what I'm going to explore in the following 2 videos.